This training module provides some motivation and insight into why numerical integration is necessary and how it's accomplished in a general Bayesian modeling framework. Here is a simple Bayesian model of normal linear regression where the model has two covariates. The posterior distribution is a four-dimensional non-standard distribution that we're going to want to summarize and make statements about. We'll likely want to calculate posterior probabilities, get Bayes estimates that are really posterior means. Possibly we'll want to derive the predictive density and then make calculations with predictive probabilities. These high-dimensional integrals are intractable, and this is the reason why, even though Bayesian models were conceived of in the late 1700s, more than 100 years before p-value based models, they were not generally used. No one could do these integrals in practical problems. In 1953, Nicholas Metropolis published a landmark paper called Equation of State Calculations by Fast Computing Machines. And in 1970, W.K. Hastings extended this to the more general case. For those of you not around in the 1970s, computers had very little memory compared to what is available and were quite slow. Since the late 1990s, computing power and software has made the Bayesian models viable because now we can work through these integrals without nearly as much trouble. This slide deck is not meant to be a comprehensive treatise on numerical integration, but is really only to serve as an illustration of why numerical integration is necessary and how it can be performed using the Metropolis-Hastings algorithm. Since this is the most commonly used approach, statisticians will generally experience fitting Bayesian models with the software that's readily available today. In general, a posterior distribution will be multidimensional. So the illustration I put together here uses a bivariate normal as the target distribution. We can generate bivariate normal data directly quite easily, but for this illustration, we'll be generating it using the Metropolis-Hastings algorithm and then compute the probability of the event that you see at the bottom of the slide that divides the bivariate space by the parabola. Essentially, all the algorithm does is draw samples from whatever the target distribution is that we can specify up to a proportionality constant in however many dimensions we have. After we have a suitable number of draws, then we can compute quantities of interest, and these are always the result of the evaluation of some integral. So this illustration easily generalizes to any Bayesian modeling problem. This graph shows the contour lines of the target distribution, the bivariate normal, that we're going to sample from using the Metropolis-Hastings algorithm, and the shaded region that represents the event that we're interested in. This problem does not have a closed form analytic solution, just like almost all practical Bayesian problems we will encounter in a clinical trial setting, so it serves as a simple example on how we can obtain the results we need by numerical integration methods. The theory around the infinite state Markov process that makes the Metropolis-Hastings algorithm work can be investigated at any number of sites online, and the purpose here is not to dive deeply into the theory. Boil down its essential elements as we pick a starting point, and that's where the process starts. That can either be done randomly or arbitrarily set to a constant. In the next step, a move is proposed according to some random distribution that's conditional on where we currently are, that is easy to sample from. We then move to this new location, depending on its relative likelihood according to the target distribution we're trying to sample from. If the point is more likely, then we move automatically with probability 1. If it's less likely, then we move with probability commensurate with how less likely it is. Finally, we keep a tally of everywhere we've been and stop once we've accumulated enough points to attain the desired accuracy and the quantities to be estimated. Here we're starting the process at x equals 100 and y equals 100. We could have started at any place, so I picked these numbers arbitrarily. The proposal distribution G consists of two independent uniform distributions that are centered on whatever the current value of x and y are. So in this case, they're centered at x and y equals 100 and can sample between 95 and 105 for both x and y, because they allow for values up to plus and minus 0.5 from the current location. We then compute the likelihood ratio of where we're going to based on the target density that we're trying to sample from, along with the probability of accepting the proposal. If the new spot is more likely with respect to our target density, then we go to the proposed spot with probability 1. If the proposed spot is less likely than our current location, then we go there with probability in relation to how less likely it is. So if it's 10 times less likely, then we go to the new spot with probability 0.1. This process continues until we're able to estimate whatever we're trying to estimate well enough to be satisfied with the precision of that estimate. What we see here also is an example of how this process meanders through this bivariate space. We start at the point of x0, y0, and you can see we move into the heavier part of the density, and then we'll stay there throughout the simulation process. This animation shows the progress of samples as we start the process at x equals 100 and y equal 100, and then take 100,000 draws from the target distribution. As you can see, as this simulation fills out there, we have this bivariate normal, and that's our target density. So this is exactly what we would expect. This output represents the results from a draw of 50,000 samples from the target distribution. The true mean and standard deviation of the x variable are 45 and 10 respectively, and for y are 70 and 20 respectively. The true correlation is 0.8. So we see this is the quality of the estimate that we get from 50,000 draws. In the case where we have more draws, we get better estimates, just as we would expect. So the parameter estimates are going to be more precisely estimated. This could be done, these sequences can be done arbitrarily long for whatever precision is desired. I used ProcIML to run this Metropolis-Hastings algorithm, and I'll go through this code with you now. Here we set the starting point for the simulation at x equals 100 and y equals 100. This block of code represents the 200,000 draws that we're going to take from this target distribution. It's a loop, and within this code, we calculate the likelihood. There's our likelihood function of the target distribution, or actually log likelihood of the target distribution that we're going to be sampling from. Here's our proposed value, x1 and y1. We see that they're uniformly distributed. They have a width of 10, so they're plus and minus 5 on the current values, x0 and y0. We calculate their log likelihood. At this point, we calculate the probability of accepting this proposal. So we calculate the probability of accepting it, and then we generate a uniform random, because either we're going to accept it with that particular probability or we're not. And if we do accept it, then our current location, x0 and y0, are the proposed value of x1 and y1. We then update the history, meaning that we're accumulating this information. We create a data set from this matrix of values. And so then we bring this into a SAS data step and create the event that is the probability event that we're trying to calculate the probability of. And this is an indicator variable, so every single time that this condition is satisfied, the event takes on the value of 1. Every other time it takes on the value of 0. And then all that remains is that we take the mean of the event variable and we get this probability of 0.4429. So we can calculate the margin of error, which is a reflection of how accurately we're able to estimate this probability. And we see that for this particular probability with this number of draws, we have a margin of error of 0.002. If it needed to be more precise, then you could just take more samples. So the probability of the event that we're interested in here is 0.442, the shaded region, according to this bivariate density. So this is how the Metropolis-Hastings algorithm works. You sample from this target distribution. It doesn't have to be a known distribution, and that's right up the alley of all these Bayesian posterior distributions that are non-standard or unknown multivariate distributions. And then it's a pretty simple algorithm to then calculate whatever quantity of interest with whatever degree of accuracy that you're interested in. ProcMCMC does this all behind the scenes, and all that remains at that point is to assess the diagnostics to make sure that you're actually in the target density and that you can believe the numerical integration results. That's a separate training on diagnostics. So there you go.